Hello? Are we alive? Is everything on fire? I hope not. I hope everything's going good. Well, we're going to start off tonight with a little bit of a reaction. And we're going to react to the 20 Games Challenge video.
Welcome to
So let's switch over to that and get started.
the 20 Games Challenge. Let's
Getting,
assume you want to learn to make a video game.
we do.
Where do you begin? Obviously, you'd probably start with a tutorial, but let's say you've put in your 2 or 6 or 40 hours, however long it took to make something extremely simple.
Let's say that you finished watching all of my videos and you put in the 5 or so hours needed to make something rather simple.
And now you have the most basic mechanics of the game engine you're using under your belt, but you are not by any means an expert. What comes next? A lot of people will move straight into their dream game.
So, thought on this. Not to crush anybody's dreams, but the idea of a dream game is kind of silly. Because your dream has this really weird habit of changing on you all the time. This dream to learn how to draw a triangle? Terrified. I know, right? Your dream game changes on you all the time. One day you dream of something, the next day you see something cool and it goes into your dream game. The dream games have this really nasty habit of growing bigger and bigger and bigger. And so how much time do you want to devote to this thing that's going to grow bigger and bigger and bigger? Instead,
The reason why they
follow
wanted
this
to learn
something
to
like
make video
this.
games in the first place. Unfortunately, video games are really difficult to make. They
Max.
are much easier than they've ever been before. We are in an amazing time if you want to learn, but it's still difficult. And the majority of people fail to finish their first project that they start. So, what do we do about that? If you ask around the internet, you will start to get the same advice over and over again.
And that advice is to make a bunch of small games. But small games are kind of boring, right? So the 20 Games Challenge is like an idea of here's like a set path, make these games, and they will walk you through learning the basics of stuff and then build on top of each other until you've learned how to make games.
Start small, make multiple projects, and work your way up to something big. Maybe instead of making that dream game, you're going to start with some other idea you have that you're not as committed to, but it should be easy, right? The one problem is, if you don't know how to make a video game, how are you going to know how to estimate how big a video game is?
I've fallen into this trap a few times. When I was starting out, I was like, I'm going to make a card game. Card games are easy, right? And then proceeded to spend the next 5 years of my life working on card games. Small games are great, they are. Estimating how big a game is really hard though. So what exactly is a small game?
How are you going to know that this idea you have is actually small instead of just seeming small on the surface? And what happens when you find yourself 2 years and 3 prototypes into a project that you didn't really care about to begin with, but you just thought it was small and it turns out it's not? There is one other option that a lot of people are interested in, and that is game jams. Essentially, if you want to learn to make a video game, you can hole yourself up in a room for 24, 48, or 72 hours and just do what you know and make something. And
Just sit in a corner and have no life for a weekend and have no sleep and then be screwed for the whole next week? Game jams are not for everybody. Game jams are not for AI.
get it out there in front of people. At the end of the jam, you have finished a project. And that's great. It's not for everyone. Again, if you don't have 24 or 48 or 72 consecutive hours to dedicate to a jam, you might not even be able to do that, but it does work for some people. So is that our only option? Game jams, only way to learn games? No, there is another option that a lot of people do, but not a lot of people talk about, and it hasn't really had a fancy name, which is why I decided to make a website about it. That idea is recreating games that already exist.
So the idea here is that when you go to art school, They're gonna have you draw a lot of things that exist. They're gonna have you draw a fruit. They're gonna have you do an art study to copy like some artist. Artists do this idea of a study all the time. Well, if a game is an art form, why don't we do game studies? Where our goal is to copy some existing game. Maybe a vertical slice, a small piece of it, but why not start by copying some of the classics?
And that'll sound weird to a lot of people who might want to get into games because they want to express their creativity. But if you want to be creative, you need to at least know the fundamentals. This isn't about unleashing your inner Picasso, it is about learning to hold the paintbrush. The goal of the 20 Games Challenge is not necessarily to make 20 games, although you can. The goal is to learn game design in 20 games or less. Now, again, 20 games sounds like a lot, but ask yourself the question, if you were going to learn to play an instrument, how many songs would you have to play? If you were to learn to draw or paint, how many drawings or paintings would you have to make before you'd consider yourself good enough to make art that other people will take seriously? So that's what this challenge is about. You are starting with fundamentals. The idea is for this to be very flexible. So if you have ideas, if you want to mix things in, if you want to do game jams, that all works. You don't have to be locked in. This isn't a class. This isn't a tutorial. Really, this is the syllabus.
It's just a set of steps to follow, and if you kind of loosely follow it, it'll help build you up to being able to make fun games. Like the very end games are suggesting you make something difficult like Minecraft or Portal.
That you can take and adapt and use on your own. The way you'll do this is you'll go to this page. There is some help. There's some how it works. A few things to get you started. The main link here is the challenge page. There will be a list of 10 games. Actually, there will be a list of much more than 10, but they will be in tabs, and you're going to take them one at a time. So if you want to start, you start here at game 1, and you can pick. You want to make Pong, Flappy Bird, Doodle Jump. I just have 3 games for now. I may add more in the future. But you pick one of these. Let's say Pong. And you have a fixed goal. If you can accomplish these things on the list, if you can make a arena with 2 paddles and a ball that bounces and it tracks scores when you exit one end of the arena or the other, you have made Pong. And you can say that you have successfully completed this video game. And here's a difficulty estimate, how complex it is. That means what is the technical details you're going to need. Scope is how much stuff you're going to make. Are you going to be making a bunch of...
So he's done the hardest part for you. As Mode said, is that how you say your name, by the way? Anything that can be done in 1 or 2 weeks is small. But if you've not made a game yet, how are you supposed to know if something will take you 1 or 2 weeks or not? Maybe a maze game would be easy, right? But maybe you have to implement a physics system. And maybe that has a lot of wrinkles that you weren't prepared for. How do you know if something's hard or not? Well, he's gone through and analyzed a lot of existing games and then sorted them by difficulty for you. And then added in like some very concrete goals for what you should be trying to accomplish and what you should be trying to learn from each one.
art? Are you going to be making your own music? Are you going to be drawing things? Are you going to be making sprite work? All of that adds to the scope, even if it doesn't add to the complexity. So complexity means you're going to have to think hard. Scope means you're going to have to work hard. But combined, that's going to tell you how big these games are. You can expect to be making a lot of these first games in, I'd say, 20 hours or less, assuming you have some basic knowledge of, you followed a tutorial once before. It can be a lot longer, and that's okay. The thing is, this can be flexible. You can learn good habits. If you want to do 1 hour a day, and when you finish a game, you move on to the next one, that's okay. If you want to try a game in a weekend, you can try that too. But the idea is to slowly build your way up by recreating classic games. And when you're ready to jump off that train, if you say that you know how to make games when you're done, then you've completed the 20 Games Challenge. So if you go all the way down to the bottom, you might be trying to make Doom or Mario Kart or Minecraft. And that may sound impossible if you've never made a video game. But if you start at the top and you walk your way down, you will gain the steps you need as you go. Game 2 actually builds directly on Game 1. If you've made Pong, the next step, you can go to Breakout.
And that's one of the really nice things, and why I think this is like the way to learn how to make games. Not only has he sorted them by difficulty, he's also tried to pick things that build on top of the previous things. So you can kind of describe Breakout as Pong, but there's like blocks you have to break, stuff like that. So a lot of what you want to, a lot of the foundation will already be there when you go to the next game.
And that one is Pong, but with extra steps. The complexity doesn't even really change. You just have a little bit more scope, and you just need to add some things to the game you already made, and you get a new game. From there, maybe you're going to start completely over if you want to make Frogger. Eventually, you'll get to things like Pac-Man and learn how to make some basic AIs. Again, this challenge is not a tutorial. I'm not going to be teaching you how to make these things. And really, the idea is that you don't look at a tutorial. If you have questions, look on the internet in general, find answers. If you really need to look at a tutorial for this game in particular, watch it all the way through. Don't go step by step because that isn't really the same thing as learning. But watch a tutorial, set it aside, come back to the game, work on it, or find specific questions online. Learning to Google is a huge skill for game design. So if you can answer those
Learning how to look things up is like the biggest skill in all of computer science, not just game design. Half of computer science is just copy and pasting things together that you read on Stack Overflow.
specific questions without finding a tutorial for this game in particular, that'll help. But the idea is that you're going to be working your way up. Once you've completed the first 10 games, then you're going to move into phase 2, which is
Bad Nabu. Get out of here with the prompting LLMs. Don't teach people bad habits.
Game 11 and beyond. You will have a much larger list to select from. The idea is to figure out where you want to go. What kind of games do you want to make? Are you interested in making a real-time strategy? Well, maybe we're going to start with a tower defense and we're going to work our way up, but you've already made a first-person shooter, so you have a lot of experience with games. You're going to work your way in. So you can tailor this however you want. You can add in your own projects. If you want to do a capstone, if you want to make something completely original partway through, once you realize you know how to estimate the scope, you can start doing that. You can throw in game jams, like whatever works for you works. But the idea is that this is a free resource I'm putting out to help people learn to make games in the way that I learned. And it has been extremely useful for me, so I hope it is for you.
And AI also hopes that it winds up being useful for everybody. I decided to pick this video now because we're starting to shift out of the generic computer sciencey type topics. I'm starting to shift more into like the real game design topics tonight. So I wanted to react to something that would kind of have like a guiding star for us. The idea for this channel going forward is we're gonna do the 20 games challenge. We're gonna make a bunch of games and we're gonna learn all the techniques to do it along the way. So why not start off at the very beginning and show what we're working towards?
Transparency, I am on game number 10 currently. I have been thinking about and developing the challenge as I've been making games. I am actively working on the website. I actually don't have all the games filled out at the time of making this video, but I am trying to get them done as quick as I can. I haven't made all these games, but I will be estimating complexity and scope based off of the games I have made and doing research. I'm going to have a little bit of background information on each game and some other stuff. One final note I do have for feedback. This is going to be free and open source and all that stuff. So if you are interested in helping make the website great, feel free to either jump in on GitLab or hit me up on Discord. If you are interested in doing the challenge, I would love to hear how that goes for you. If you are making devlogs or tutorials on your own, either video or blog.
Well, so the rest of the video is just shilling feedback stuff. And hi, Voids. To answer the question, I have. And in fact, I've tried quite a ways beyond Vulkan. Have you tried WebGPU? Have you tried Metal? But tonight, we're not doing anything particularly complicated. Tonight's goal is the simplest thing possible. We have a computer, and we would like to draw a triangle. So how can we go about doing that? Well, we're going to start off by pulling up my notes. I am totally a giant cheater. I cannot remember everything off the top of my head. Ba-ba-ba. Cool. So we're going to start off by talking about what a GPU is and why we might want to use a GPU as a game developer. So inside of your computer, there are two main components. There is I like how I start drawing and forget to put on my drawing equipment. There is a CPU, a central processing unit, and there is a GPU, a graphics processing unit. And it turns out that the GPU is just a really good vector math machine. Vector math slash linear algebra machine. So a lot of techniques in the video that went up on Saturday about math are like really fast to run on a GPU. The GPU is super well optimized for running those vector type tasks. Just a lot of multiplications on lots of things at the same time. Whereas the CPU is a little bit more general, but it's also a little bit worse at being super duper fast. It has a few powerful cores. So we're talking 4 to 8 nowadays that are really good at all sorts of stuff like if statements or doing loops or doing complex calculations, whereas a GPU has usually thousands of weak cores. So they're all really good at doing approximately the same thing to a lot of stuff at once. And each one of them is a tiny bit slower, but when you start being able to do thousands of things at the same time, it works out. I'm completely new to game development, so can I join the stream or is there some prerequisite? Well, the recommendation would be that you at least know a little bit of C++, because we're gonna jump into some C++ code here in a few minutes. If you happen to not, I have a couple of videos and shorts on this channel on the subject that might be helpful. Or if you just like to stick around and passively absorb some knowledge, that works too. So the CPU has a few powerful cores, and the GPU has thousands of really weak cores that all have to do approximately the same thing. So what we do is we send commands. So there's a little stream of data that flows from the CPU to the GPU that instructs it on what it should do. And we need some sort of interface, some sort of fixed standard for defining how we might move those things around. Let's talk about a couple of those fixed standards. So the most commonly known fixed standard at the moment, I think, is called Vulkan. Vulkan is kind of the new kid on the block. It's been getting a lot of hype recently. Oh, well, I guess we're taking a brief hiatus to ban a bot. Here we go, ban. Cool. So, Vulkan is a replacement for OpenGL. What we're going to talk about tonight. So, if there's been a replacement for something, why am I teaching the old thing? Well, the short answer to that is that to do what we're about to do tonight in about 100 lines of code, in Vulkan will be about 1,000 lines of code. So Vulkan is approximately 10 times harder than OpenGL. There's also some argument that Vulkan is faster, but my mic suddenly got choppy. Well, that's great. Is this any better? Mic check, mic check. Yang, it's fixed. Cool. So, Vulkan is about 10 times harder than OpenGL is. So, we're going to start with the easier thing. And I recommend for learning purposes, it's better to start with the easier thing. Part of why Vulkan is faster is that it gives you more control. But if you don't even know the basics, what is that more control going to give you? Right? So it's better to start with OpenGL or something simpler. There are a couple of other alternatives that are common. One of particular note is DirectX, and DirectX is the Xbox graphics interface. It defines how you would communicate with the graphics cards on the Xbox, or it's also the Windows interface. So it's how you would communicate with graphics cards on Windows. Problem is it's Windows specific, whereas Vulkan and OpenGL are cross-platform. Asterisks. If you happen to be on a Mac, Mac does not technically support either one, but there are emulation layers on Mac that will work for both. Mac used to support OpenGL, but then when everyone switched to Vulkan, Mac was like, okay, we're going to get rid of OpenGL support. And we're not actually going to use Vulkan. We're too cool for Vulkan. We're going to make our own thing called Metal, which is the Mac-specific graphics driver. However, there are emulation layers for OpenGL. It's called Angle, and Vulkan. It's called Molten VK that run on top of Metal. Technically, I believe Angle runs on top of Vulkan, which can run on top of Metal, but potato, potato. So let's go back to that idea about there being a CPU that sends commands. So we're going to draw a little box command over to a GPU. Well, it turns out that the CPU and the GPU are rather far apart. There's a lot of distance between them. It's imperceivable to a human, but in computer time, right, it takes almost an eternity in order to get information between the two. So every command that we send is going to take an eternity to get to the GPU. Nothing for us, but when your goal is to render 16 million pixels 60 times a second, even a tiny bit of time starts to add up, right? So the idea with like Vulkan and DirectX and Metal is that we want to pool all of our commands together. We want to make like buffers, as they call it, of our commands, and then try and send them all at once. OpenGL is all about manipulating some sort of state. So you set the state of the GPU. Turns out that that's quite a bit slower, but you can also get a default state. So it's quite a bit easier to get something up and running. Sound good? So what are we going to talk about today? Well, before we can get started with sending commands to the GPU, it would probably be good to have something to draw on, right? We would like a canvas. So we're going to start off today by creating a window. We're then going to load OpenGL. OpenGL is a little bit different than most other libraries. We're going to talk a little bit today about libraries, but OpenGL is weird because there's different implementations on every platform. Like the way OpenGL works on an NVIDIA graphics card is going to be different from how OpenGL works on an Apple Silicon graphics card. So we have to be able to support all of those. So we're just given some interface, and then we're able to code against that interface, but we have to load the specific implementation that our system uses. So after we've created our window, we're going to load. Hello. Would you like to be a little bit more cooperative? There we go. So we're going to load OpenGL. Will I be teaching how to make a render? Do you want the long answer or the short answer? For tonight, no. But yes, the goal, like I said, the goal of this channel is we're going to be working through the 20 games challenge. And we're going to be trying to learn everything necessary to make games along the way. So we're going to learn about rendering. I'm probably going to go on some tangents about software rendering at some point. We're going to learn like all the techniques that simple games would use. And given enough time, we're going to maybe loosely historically build our way up to where we are today. We're definitely going to talk about PBR. We're going to talk about some stylized rendering. I don't know. We're probably going to talk about tessellation and how tessellation would work. And we're probably going to talk about the new meshlet rendering style that's been in vogue recently. So how stuff like nanite and variations of nanite work. But tonight's goal, we're not going to be making a full renderer. We're just going to draw a triangle. And so we're going to learn all the components of OpenGL we need to just draw a single triangle. Sound good? So, without further ado, we're going to pop over to code, and we're going to start getting an environment set up. As we wait. And we wait. So, we're going to start by creating some folder somewhere. I'm going to create a folder in Documents, and I'm going to call it OpenGL in OneStream. So, in here, we're going to open Visual Studio Code. If you have no idea what I'm on about, go watch the C++ in OneStream video, which will start off by introducing how to set up all this stuff. It will also introduce how to create a Hello World file. So we're going to do that real fast. In main, and we're going to print out Hello World. Now we're going to make a CMake file, which we will use to tell the C++ compiler what we should do, how we should build this project. We're going to say that we're using 64-bit code. CMake minimum required version 3.21. We're going to make a new project, which we're going to call OpenGL. And it will be a C++ and a C project. Then we're going to add an executable, which we're going to call OpenGL. And from this, we're just going to go hello.cpp. So if we now build, it's still figuring stuff out. If we now build this and give it a quick run, the most basic part of our environment, having C++ work, should be there. We should be able to say hello world. What if I made the font like 3 times bigger? Well, then things become a little bit harder to read, no? Well, harder to fit in one place. Does this make you happier, Nabu? So, we're now going to go and download a couple of things. So I mentioned we're going to need something to open Windows. So we're going to go and download something called GLFW, which is an open source OpenGL windowing library. So we're going to go to their GitHub page, and we're going to go to this green code button and download a zip file of all their source code. At some point in the future, I'm going to do a video discussing what Git is and how it can be used to manage libraries, but that is not the goal of tonight. The goal of tonight is that we're going to open up this folder again, our code folder. We're going to make a new folder called third party, and we're going to use this folder to store all the stuff that we didn't make, so all the libraries that we use. So we'll drag GLFW in there. And then we're going to need an OpenGL loader. So we're going to look up GLAD OpenGL. Go to the first link, and he should link to a generator. So we're going to generate a C++ loader for OpenGL 3.3. Newer versions than 3.3 have spottier compatibility, and we don't need anything particularly complicated in later versions. To make our life simpler, we're also going to scroll down to Options and select Header Only, and then Generate. This should now give us a folder we can click on, and inside of the GLAD folder, there'll be this gl.h file, which we can copy, and we're going to put into that third-party directory as a file called glad.h. For anyone who would like to follow along but is feeling a little bit lost, don't worry, VODs will be up, and shorts will be up if you prefer the shorter 1-minute version. So this file is kind of interesting. It does two things for us. First, it introduces a lot of interface. So it defines, here are all of the functions that OpenGL supports. So stuff like end conditional rendering, or rag chord, or accumulate stuff. So there's a lot of stuff in here, and we're only going to talk about a little bit of it. But the important thing that we want to talk about is this GLAD GL implementation part. So they're going to hide away the interface that loads all of the stuff from the implementation. So in one file, we would like to include third-party/glad.h, and we would also like to define this GLAD GL implementation. Hello, Mr. Cruise Boy. How are you doing tonight? Is that how you, Cruise Boy? Cruise Boy? How do you pronounce your name? You're new to Linux and trying to rice. Well, unfortunately, I am not the correct person to help you with that. This Cruise is fine? Sounds good. Since my riced version of Linux is installing KDE, which I think is some sort of heresy in the ricing community, I believe. So this GLAD GL implementation thing is going to tell us we would like to include all of these definitions for how the code should work. We don't want to just have the interface that tells us what's available. We want to actually be able to load it. So we're also then going to need to load up GLFW. So in order to access GLFW, we're going to have to add a line to our CMake script. So we're going to go target, link directories, OpenGL, public, and then third-party/GLFW. So what's happening here is we're going to take the OpenGL executable that we're making, and we're going, no, and we're going to add a subdirectory third party slash GLFW. So we're going to start off by telling CMake, hey, I'd like to load all the code for GLFW in. And then we're also going to tell CMake that I would like to link against all of the code in that library. You know the site where I can check JSON, C, and CSS before I implement it in my PSC? I do not, unfortunately. Sorry, I can't be more helpful. So if we now give this code a build, you'll see that a few more files are being built than just our hello.cpp file. And we now have GLFW alongside. So we can include GLFW slash GLFW3.h, I believe. What exactly is it? It is GLFW. Target link libraries. We don't want to link directories, we want to link libraries. We don't want to link a directory called GLFW, we want to link a library called GLFW. And that should now compile fine. So instead of printing hello world, let's get started with opening a window. So to start, we're going to have to call a function called GLFW init. So GLFW might need to do some stuff for each platform. They might need to set some flags or something. So we'll just tell them to set up everything they need to do. While we're initializing, at the end, we will also GLFW terminate. We'll give that a little compile, make sure that nothing's broken. Cool. So we've now successfully started using GLFW, but we don't have a window yet. So we'll create one. So let's make a GLFW window pointer, which we'll call window. We're going to set that equal to GLFW create window. This function takes a couple of parameters. It takes a width, so we'll set 800, and a height 600. It takes a name for the window, so hi chat, call it. And it also takes a couple of pointers. I believe this first one is to shared, like, the board type state, and the second one is to the monitor that we would like the window to be opened on. We don't really care about either of those things, so we'll just set them to null. And then what we do care about is if we can't create the window. So if GLFW gives us null back, we would like to print out an error. So std_c error, GLFW broke. And then we're going to GLFW terminate, and we're going to return -1. So we're going to return -1 to indicate to the operating system that our program crashed. It didn't successfully succeed. Successfully succeed is a crazy statement. If we run this now, it should immediately close, but we shouldn't crash. Let's also do our cleanup. So I believe that is GLFW window destroy the window. It is not window destroy. It is what is it? GLFW destroy window. Oh, it's GLFW destroy window. So we got the window and the destroy backwards. So when we run this, right, we're creating the window. The question is, why is there nothing there? Since this virtual machine is a little bit slow enough, you can kind of see what's happening. A window pops up for a split second and then goes away. So let's write a little bit of code to make sure that that window sticks around a little bit longer. So if we now write a while true in here, we should see that the window will open and we can move it around. Well, kind of, but there's a bit of a problem. You can't interact with it. I can't close it. I'm going to have Windows force close it. That's because we're never going to get out of this while loop. So we create the window and then forever we do nothing. So instead of doing nothing forever, let's do it until GLFW window should close the window. So when the user of our game decides that they would like to close the window, this will be true. We can also send some commands to close the window. So when does the window get closed? Well, it's when we click the X button. So, oh, you're still not being very interactive. I believe the reason for that is that we need to GLFW full events. And while we're at it, GLFW swap buffers. So this function ensures that the window is constantly displaying new frames. And this function ensures that if there are any events, like the user pressing the close button, GLFW is informed of them. So now we should be able to move our window around, and we can hide it, bring it back, maximize it, close it, and everything should work fine. So now that we have a window that we can draw to, we need to start setting up the OpenGL part. So we're going to tell GLFW a couple of things about our window at the beginning. We're going to tell GLFW with a window hint that we would like the GLFW OpenGL context version major to be 3, and we'd like the GLFW window hint GLFW context version minor to be 3. So remember how when we were downloading our OpenGL loader that we grabbed back up? That we grabbed version 3.3? So we're telling GLFW that we would like to make a window with OpenGL 3.3 in it. I believe for 3.3, we also have to specify GLFW window hint GLFW OpenGL profile. And we're going to say that we're going to use GLFW OpenGL for profile. There's 2 versions of OpenGL 3.3, the core version and the compatibility version. So we're just going to use the core version. Last thing we need to do is we need to tell OpenGL that the current window is what we're drawing to. So we're going to make the context of the current window what we're drawing to. We give that a compile. It should work. And we give it a run. Nothing should be different. So we have OpenGL in our window now, but we're not actually drawing anything to OpenGL. So let's start talking about how we would go about drawing. So in the math video, we talked a little bit about space. If you remember from that, we'll know that the y-axis goes down along the screen and the x-axis goes to the right. So by default, this top left corner of our window is going to be at 0, 0, and this bottom right corner is going to be at 1, 1. It's a Russell. How are you doing tonight, Russell? So everything we want to draw by default will be between 0, 0 and 1, 1. We'll learn a little bit later how we can change this up, do a little bit of math to make this space a little bit bigger. But for right now, everything we're going to do is between 0, 0 and 1, 1. And this is one of the places where OpenGL differs from a lot of the other things. Because I believe in OpenGL, it actually goes -1, -1 to 1, 1, which means that 0, 0 would be in the center. Usually 0, 0 is up at the top left, but OpenGL is a little bit different. So we got to keep that in mind for tonight. So we'd like to draw a triangle. In order for a GPU to draw something, we need to give it some points in space that we would like to draw. So let's pick a couple of points in space for our triangle. So how does like straight up sound? Well, I believe that this will be the point 0 and -0.5. Let's do that in a different color. Also, I'm sorry to hear that you're not feeling well, Russell. I hope you feel better. So 0 and -0.5. Now we'd also like some corners. So let's do -0.5, -0.5. And then let's do -0.5. 0.5, -0.5. So that would be down here-ish. What am I doing? No. So we're doing -0.5, -0.5. We're doing 0.5, -0.5. And then down here, we're doing 0.5. So let's create an array to hold those points for us. So we're going to make a good array of floats. We don't have any library with us to help us store these points. So we're going to need 3 points each. We're going to set z to 0 for all of them. So we're going to need 3 times 3. This is going to be equal to, what do we say? 0f, 5f, 0f for our first point, -0.5f, -0.5f, and 0f for our second point, and then 0.5f, -0.5f, and 0f for our third point. Now that we know what we're going to draw, it might be helpful to actually tell our loader to load OpenGL. We've told GLFW to make an OpenGL context for us. And then we would also like to tell it that we would like to load all the OpenGL functions. We're going to say, if not, GLAD load GL. and we're going to pass it the GLFW get proc address function. So if you failed to load all of the OpenGL stuff using GLFW, then we're going to similarly see error GLAD broke. And then we're going to GLFW terminate, and then we'll return a different error code. So we failed in a different way. And now we need to take our data, which we're going to call points, and we need to put it onto the GPU. So right now we have memory on the CPU, but we would like this to be moved to the GPU so the GPU can render it. So we're going to need to create two things here. We need to create a vertex array object, and we need to create a vertex buffer object. So a vertex array object defines what vertices these points look like. So in a more complicated implementation, we might have, say, a position and a color, and we might bake in which way is perpendicular to the surface, so a normal vector. We might have texture information. We might have all sorts of things stored on each of these points. So the vertex array object is how we tell OpenGL what the array looks, what a single point looks like. And then the vertex buffer object defines the memory. So we're basically just going to copy this memory that we have on the CPU and store it into a GPU array. So we can think of this as a GPU array, storing something that we've copied over from the CPU array. So let's start off. We're going to make an unsigned int, call it VAO, and we're going to ask OpenGL to generate a vertex array. Unfortunately, well, conveniently, they let us make more than one at once. But since we only need one right now, the fact that we have to do, we have to ask for multiple and then tell it, actually, when I ask for multiple, I only want one. It's a little bit inconvenient. What it expects here is a pointer to an array of stuff that we would like to fill, and then a count of how big that array is. So for us, we just have a single variable, so we'll take the memory address of it to get a pointer and tell it that we'd only like one thing. We're filling this array of one variable. Kind of abusing the idea of what an array is. Then we'd also like to generate a buffer. So we'll generate one buffer and make an unsigned int VBO. So these ints are like pointers to GPU memory. Except we don't call them pointers, we call them handles. But it's the same idea. It's a pointer to some resource on the GPU. So VAO is a pointer to the information about what vertices look like, while VBO is a pointer, quote unquote, to information about the vertexes that we would like to draw. Now, we're going to start by binding the GL bind vertex array, VAO. So we're telling OpenGL to tell OpenGL that we are working on the VAO. So this is now bound, so any modifications we make to a vertex array are modifying this bound VAO. Like I mentioned, OpenGL is kind of about manipulating state. You specify what state we'd like to manipulate, and then you just start manipulating it. With other APIs, you have to like pass things around a little bit more explicitly. I think that's better code hygiene, but it's also a little bit harder to wrap your head around, and it's a little bit more verbose. So, double-edged sword. Then we're going to tell OpenGL that we are working on the VBO. So we're going to set up the vertex buffer. We're going to GL bind buffer, GL array buffer, VBO. Like I mentioned, we're thinking of this VBO as an array on the GPU. And so we're telling OpenGL that we're thinking about it as an array on the GPU. And we would also like to bind it over to our vertex array. Make sense? So this is now set up that this VAO has some memory bound to it in this VBO. And now we'd like to actually upload some data to the GPU. So we'll tell OpenGL what data to store in the vertex buffer object. We're going to GL buffer data, similarly telling it that this is an array. And then we're going to tell it how big, how much data we'd like to upload. So we're going to go points.size. And we're going to multiply that by the size of 0.0. So we're telling it how many bytes of memory we would like to upload to the GPU. And then we tell it what data. We give it a pointer to the data we'd like to upload to the GPU. And then a little hint here, GL static raw. So a little hint about how we're going to use this data. We're going to use it to draw stuff that doesn't change a whole lot. So we're statically drawing these. I'm not going to get into details about all of the other modes here. So things other than GL static draw or things other than GL array buffer. But we can go and look at the OpenGL documentation, OpenGL reference, and we'll look at OpenGL 3. And we can look up, what are we looking at? GL bind buffer. We can look up GL bind buffer, and it tells us like what all these binding targets are. So what GL array buffer does for vertex data versus draw and direct buffer or query buffer. Make sense? So we've now told OpenGL that we would like to have some vertices and we would like to bind some data to the vertices. But we haven't told it yet what this data looks like. So we're going to tell OpenGL what a vertex looks like. So we're going to go GL vertex attrib pointer, which is kind of a confusingly named function for this purpose. And we're going to say that attribute 0 is going to be 3 elements, and they are floats. Let's look up what else it provides. It would like us to say if it's normalized or not. So are these floats between 0 and 1? Well, since we've got negatives in there, they're not. So we're going to say GL false. And then we're going to specify how far between each other each of the vertices are. So let's look at how far away each point, each vertex is from each other. Well, each one is 3 points. So if we're starting here, to get to the next one where it starts, we need to go 3 floats deep. So to tell OpenGL that we need to go 3 floats deep, we specify 3 times the size of a float. So we'd like to go 3 floats between each vertex. And then the last thing we need is a pointer to some data. But we've already set up the buffer for this, so we're not gonna give it any data. And then we need to GL enable vertex attribute array. So we're telling it that the 0th attribute is now enabled. And it has 3 floats that are spaced 3 floats apart and not normalized. Sound good? Well, there is now a problem. We should be able to run our game, which we'll put in air quotes. And I spelled something wrong. GLGen buffers and enable vertex attribute array. GL buffer. Okay, I guess MSVC isn't liking this float, so we'll just say size of float. How long have you been in the game industry? Now, there are 2 answers to that question. I have never technically been in the game industry, but I've been in academia. I've been teaching about the game industry for 5 years now. But I am unfortunately a bit of an ivory tower academic. Oh, the problem here is not this. The problem here is that in order to use stood array, we need to include array. Cool. And spell data right. Does that answer your question, Mr. El Salta? And now, when we run it, well, we still get a black screen. Nothing has happened yet. We have all this data on the GPU, and we've specified what a vertex looks like, but it still hasn't changed yet. Although we have the nice little hi chat message in the title. So why is that? Well, to understand, we need to start talking about what we call the graphics pipeline. So, what is the graphics pipeline? So, the CPU will hand data. So, we'll start with the CPU. And it will hand some data. So, vertices and their attributes. So some raw data and information about what it looks like. So we've defined that so far. We've specified what vertices look like, as well as some data to back up those vertices. And then what does the GPU do with it? How long did it take for you to get the degree of pedagogy for teaching video game development? So I'm still actively working on some of the credentials, but we're 8 years in right now, and the projection is it'll take 3 more. So in total, it's expected to take 11 years. A fun, long amount of time, right? So this data, this vertices and attributes, then get passed into what's called a vertex. Vertex shader. So we have this fun word here, shader. What's a shader? Lots of people like to throw the idea of shaders around, right? Like Minecraft shaders that make them all pretty, or shader programming or stuff like that. Well, shader is just a piece of code that runs on the GPU. So the point of the vertex shader is to specify and process all of this vertex data. For our cases, we're just going to pass it straight through. But you can do a lot of complex stuff. So terrains might take a flat plane of data and then add some complexity to it. Make sense? Unfortunately for us, we're just going to write the world's simplest vertex shader that just passes the data straight through. So the vertex shader will figure out where actually all the points in space should be, and then it will pass them to what's called the rasterizer. I'm going to probably do a video on software rendering at some point. And in that, we're going to talk in more detail about what the rasterizer does. But the rasterizer's main job is to turn triangles into pixels. So then the rasterizer is going to pass its output down to what we call a fragment shader. Some people instead call this a pixel shader because it seems to be manipulating pixels. But that's not quite right. Oh, I have the wrong thing up. Ooh. How long have I had the wrong thing? Well, I guess we'll start over since I'm not quite sure. So, no, we talked about the CPU. Oh well, we'll start over. Talked about the CPU, we talked about the shader, we talked about the rasterizer. Okay. We'll start over. So, we have the CPU, and it hands us the vertex data and the attributes. So, vertex attribute. And then we take this data and we process it in the vertex shader, which we're about to write. So we'll see a little bit more in detail how that works. And then it hands the vertices off to the rasterizer, which converts them into pixels. And then the rasterizer hands those pixels off to the fragment shader, and remember that a shader is just another word for a program that runs on the GPU. So the vertex shader's job is to take the vertices that the CPU handed us and position them in space somehow. In our case, we're just going to pass them straight through. Say the CPU did a good enough job and we're not going to mess with them. But some terrain might take a flat grid of triangles and then add some height data to them. The rasterizer will then take those vertices that have been positioned and will convert them into pixels. So it takes the triangles and converts them into pixels, which are then handed off to the fragment shader. And the fragment shader is sometimes called a pixel shader because it works on pixels. But we call it a fragment shader because its results are only a fragment of the output. They may get mixed together with other stuff, they may get thrown away. And so then the results of the fragment shader are then handed off to the clipper, which decides should they be thrown away, should they be kept, stuff like that. There's quite a few tests that happen here, like stencil testing, which is kind of weird. Depth testing is there something else that should be drawn on top of this, and other tests. But the idea is if it fails the clipper, the fragment doesn't become part of the final pixel. That's why it's called a fragment, because the pixel may not be the final value of that pixel. Make sense? So we need to create some shaders. We need to make a vertex shader and a fragment shader, and we're going to use those to manipulate the color of our triangle. So let's make a new file, which we're going to call vert.glsl. And we're going to make another new file, which we're going to call frag.glsl. So GLSL, there happens to be an extension for it in VS Code, which will give us some nice highlighting, I believe. And GLSL looks a lot like C. So it starts with a void main function, very C-like, but we have a little bit of a difference at the top. So we're going to start off by saying version 330 core. Since we said that we're using OpenGL 3.3, we need to tell OpenGL that it's using version 330. We take the OpenGL version, drop the dot, so we start with 3.3, drop the dot, and add a 0. If we have OpenGL 4.6, we're using OpenGL GLSL version 460. So 330 core. And then we need to make some variable. We're going to make an in vec3 called position. But we need to tell this vector3 what attribute it should be pulling from. The in thing here tells us that since this is a vertex shader, we're pulling it in from the CPU. And we're going to say layout location equals 0. So what did we bind to location 0 in the vertex array? Our 3 positions. So we have 3 floats, a vector 3 in GLSL. It also gives us some stuff built in for matrices and vectors. We've done some work in the past videos for building some of that stuff. And then we're binding it to vertex attribute 0. And now, what would we like to do with this position? Well, there's a built-in variable called gl_position, which specifies the output position that the vertex is producing. And we're just going to set that equal to vec4 position and 1, since it's expecting this output position to be in homogeneous coordinates. Cool. Isn't that easy? A pretty simple C-like language. I'm not going to go into super detail about all the built-in variables, like GL position. But of course, OpenGL GL position, the OpenGL reference should have more than enough information about all the various different built-in things, like GL point size. So our vertex shader just takes the data from the CPU and forwards it straight onto the rasterizer. So then once the rasterizer has turned it into pixels, what are we going to do with them? Well, we need to specify that we're still using version 330, and then we'd like to specify an out vec4 rag color, or just color. So in that we're going to pull the data from the CPU. Out is telling us that we're going to push the data back to the CPU. So the output of this is some vec4 color. This vec4 is stored as RGB A, the red, green, blue, alpha. So we need to set what the red, green, blue, and alpha of all these are. So void main, and then we're going to set color equal to a vec4. And for this demonstration, I picked 226.0 over 255, 81.0 over 255, 24.0 over 255, and 1.0. So this should be an orangish color, right? Because we've got quite a bit of red, a little blue, and a little green. That should be a nice orange, and it should be fully transparent. So it shouldn't blend at all with any of the other pixels, any of the other fragments. So how do we get these files into our code base? There are some more complicated ways. There's whole like libraries that can embed the code, but we're going to do it in the simplest way possible. We're going to include string, and we're going to make a std string vertex shader. This is going to be equal to a string, and it will contain our raw data. We're going to introduce a new concept here called a raw string. So if we prepend our string with R, then inside of here, we can specify a starting pattern, so GLSL, and then an ending pattern. So anything in the string between these two GLSLs will just be in the string. It doesn't matter if there's blind breaks or tabs or whatever. Anything in there will become part of the string. So what are we going to put in there? Well, the source code for our program. And then we're going to do another version, the string fragment shader. Then we're going to copy in the source code of the fragment shader that we wrote. Cool. So how do we tell OpenGL that we would like to use these shaders? Well, for starters, we're going to go and create a vertex shader. So we're going to go unsigned int vertex shader is equal to GL create shader, and it will be of type GL vertex shader. Then we need to tell OpenGL what the source code of this shader is. We're going to go GL shader source, and it's for the vertex shader. We're going to give it 1 bit of source code, and that 1 bit of source code is vertex source.cstring. This function is expecting a pointer to the data associated with the string. So the cstring function happens to give us a pointer to the data associated with the string. And then it wants one more null pointer. Let's go look up real fast what that one more null pointer is. And it's the length of the string. Since we have a null terminated string, we can just say null pointer and have OpenGL figure it out for us. So then we have our vertex shader. We need to tell OpenGL to compile the shader. So give it the vertex shader. And now we need to create a fragment shader. We're going to do a lot of the same things. We're going to go unsigned int fragment shader equals GL create shader GL fragment shader, and then GL shader source. We'll actually copy this over and pass the fragment shader and vertex source fragment. We'll pass the vertex shader and the fragment source vertex source. And then we would like to compile our fragment shader. We'll do that real fast. And then we mentioned that the pipeline involves both of these things. So we need to combine both of these shaders together into one pipeline program. So we're going to create a pipeline program. So unsigned int program equals GL create program. And then we're going to attach both of our shaders to it. So GL attach shader program vertex shader. GL attach shader program fragment shader. And now we're going to GL link program with this program. We're going to take the compiled code for these two shaders and link it together into this shader pipeline. And after this, once the shaders have been linked, we don't need the shaders anymore. So we can GL delete shader, vertex shader, and GL delete shader, fragment shader. Cool. So if we give this a build, hopefully we won't get any errors. Hopefully I didn't make any typos. Damn. On line 80, it says it can't convert this. Oh, it wants a pointer to it. They're going to go char pointer temp equals the C string, and then we'll pass it a pointer to temp. Because we want to pass it an array of pointers. And then we'll do the same thing here. We'll say temp equal to the fragment shader, and then we'll pass it the memory address of temp. Kind of abusing the definition of an array here somewhere. Still can't convert. Is it wanting this to be char pointer? Well, let's just cast it and tell it that it should be fine. Did you study directly video game development, or did you study CS first? I studied computer science with an emphasis in film, actually. So I didn't directly study game development. I studied graphics programming for film. But there is, and then I happened to find myself in my teaching career falling more into the game development side of things, since turns out more people are interested in making video games than are interested in making movies. And let's get rid of the erroneous E's in there. Cool. So now, if we run this, we should get another black screen because we've uploaded data to the GPU. We've created a program that tells the GPU what to do with that data, but we haven't actually told the GPU to do anything with that data yet. So every frame, before we show every loop through the array. So this while loop is now going to be representing the frames of our game. This function, GLFW swap buffers, presents a new frame to the window. So every time this function gets called, we show a new frame. So every time through this loop represents a new frame. So inside of this loop, we're going to be doing our drawing every frame. Sound good? And we're going to start off by telling OpenGL to clear the screen. But we don't want to just clear the screen to black. Let's clear it to something a little bit more interesting. So we're going to set GL clear color to 28F over 255, 77F over 255, and 215F over 255, and 1.F. What do they teach in that CS oriented to film? There's a lot less emphasis on gameplay stuff, and you have a lot more time. Because think about it. in games, the goal is to render a new frame every 60 seconds, right? Whereas in film, the goal is to render a new frame. I don't know. It doesn't really matter how long it is. Like a lot of the Pixar movies can take a whole day to render one frame. So in games, we use a lot of what's called rasterization, where we take triangles and we convert them into pixels. And then we have a lot of fake techniques based on rasterization to look nice. So we kind of emulate this thing called the lighting equation that tells us how to draw. Whereas in film, you're able to do a lot of ray tracing. You're able to get a lot more better simulations of how light works, but it takes a lot longer. But when you have your budget of it, it can take 2 days to render one frame. Doesn't really matter how long your pretty math takes, right? Whereas in games, you're a lot more restricted. You have to spit out a new frame every 16 milliseconds or so. Does that difference kind of make sense? So we're telling OpenGL that we're going to clear the screen to kind of a bluish color. And then we're going to tell it to actually clear the screen. We're going to GL clear the GL color buffer bit. And now if we run our game, fingers crossed, we will not just have a black screen, but we'll have a blue screen. So where are we? An hour and a half into tonight's stream, and we actually have a little bit of something being drawn into our window. So now let's do the fun part. We're going to draw our triangle. So we're going to GL use program, shader program, and we're going to GL bind vertex array, our VAL, our vertex array object. And then we're going to GL draw arrays. So we're going to tell OpenGL that we'd like to use this program to draw everything. And then we'd like to bind this vertex data to that program. Like VFX and CGI stuff? Yeah, exactly. Although just describing visual effects and computer-generated imagery, it's applied to both. But games have more of a focus on game design, right? So what makes a game fun? And having to do things fast. So we had to do a lot of approximations in games. Whereas in film, you don't care at all about what makes a game fun. And you don't care at all about how long you're taking to render. I mean, you do a little bit, right? Because if you take like a week to render a frame, like the people at Disney probably aren't happy with you. But your constraint isn't as intense as it is with a game. If that makes sense. And then once we've bound the program, the shader programs that we're going to use, and bound the vertex data that we're going to use, we're going to actually draw as a triangle rather than lines or points, starting at 0 elements into the vertex data, and we're going to draw 3 elements of the vertex data. And now, if everything goes right, and I'm not going to be sad, we should get compiler error, because I apparently triangles. We're going to draw it as triangles, not triangle. We should get an orange triangle drawn on top of a blue background. So someone asked a little bit earlier about Vulkan, right? So let's do a line count on how many lines of code we're using. And actually, quickly, before we do that, let's clean up after ourselves, like good people. So we're going to GL delete vertex arrays. So we're going to delete one vertex array, our vertex array object. We're going to GL delete buffers. We're going to delete one, our vertex buffer object. And we're going to GL delete program, our program. And now, just to confirm that everything is working right, we should be able to close our program and nothing, our game, we're going to put air quotes around game, and nothing should crash. And now let's do the line count of this program. So to draw a triangle, we need, what is that, about 20 lines of OpenGL, of GLSL, the OpenGL shading language. And then we need, what is this, 120? So 120 minus 20, so about 100 lines of C++. Let's go over and look at Vulkan tutorial. And let's scroll down to the drawing a triangle part. And let's look at how much code they're using to draw a triangle. I believe at the bottom of this website, they should have the full C++ code as well as the full vertex and fragment shaders. So let's grab the Vulkan code. We'll make a new file here, vulkan.cpp, and paste that in. Immediate observation, it's a significant amount longer. Instead of our 100 lines of C++, it's 958 lines of C++. It's a slightly different style, so they might be writing it a little bit longer than I did. I tend to have a pretty terse style, but still, differences in style aren't going to make up a 10 times difference, right? And then they technically are using slightly more complicated vertex shaders and fragment shaders, but it's still probably about 40 lines of GLSL. So this is one of the big reasons why I'm starting off by showing everybody OpenGL, because we have 100 lines of code to get something working versus 1,000 lines of code to get something working. And then, of course, if we mess something up in here, right? It's like we do a 2 instead of a 3. A lot of the mistakes we make will wind up just giving us a blank screen. No error messages, no validation, just nothing's drawn. So trying to debug what went wrong in 100 lines of code is going to be a lot easier for somebody than trying to debug what went wrong in 1,000 lines of code, if that makes sense. So how might you go about debugging some of these things? I'm probably going to go into detail of this a lot later on, but there's tools like RenderDoc. And if you have an NVIDIA graphics card, NVIDIA Insight, which can be used to debug the shaders that are running and see all the API calls like OpenGL or Vulkan that are running. So you get like this big list of all the commands that are getting run. And you get to see it like what's being drawn and all the inputs that are being passed to the GPU and stuff like that. Gives you a lot of tools to help you debug what's going wrong. But I rattled on about graphics programming for an hour and a half now. I'm getting a little tired. Are there any questions before we end it for the night? And don't worry if anyone felt like they missed anything. I know I went really fast. They're going to be an edited VOD, probably Monday-ish, sometime between Monday and Wednesday. And then shorts from the VOD should start going up in a week or two, hopefully. All good here? Well, If there are no questions, I'm going to disappear. And for all the Twitch people, we're gonna go figure out who we're gonna raid real fast. Thank you everybody for stopping by. I appreciate you all being here. Thank you. Good night.